Good morning. This recording is for Algebra 1, Chapter 10, Lesson 1, Simplifying Radicals. Radical expressions have square roots and are read the square root of the quantity of whatever's inside. So simplifying radical expressions by removing perfect square factors from the radicand. And so a square root has a radicand inside. Square root, stuff inside the square root. There you go, that's the radicand, and that's the square root, also known as the radical. So, radical. It's radical, dude. There you go. There's your 80s reference, pop reference for the day. All right, moving on. So, multiplication property of square roots. If you can break up the radicand into two numbers that are multiplied together, you can then break them down even further. And just remember that radicands must be positive factors for the case of this class anyway. Okay, we're not going to talk about I, so don't bring it up. Okay, so if I have the square root of 54, I can break that up into the square root of 9 times the square root of 6, because 9 times 6 is 54. But the square root of 9 is a perfect square, which means I can actually square root it and get a whole integer, or an integer out. So the square root of 9 is 3, which leaves me 3 times the square root of 6, which is my simplified answer. All right, there we go. There we go, there we go. All right, so let's talk about removing perfect square factors. If I have negative 5 times the square root of 300, I can break 300 down into the square root of 3 times 100. Take the square root of 10 and 3. Well, I can only really take the square root of 100 because it's the only thing that's a perfect square. 3 isn't, so I have to leave it inside the square root. And I'm going to get negative 5 times 10, because the square root of 100 is 10, and I'm left with negative 50 times the square root of 3. That is the more simplified version. All right? So, be on the lookout for perfect squares. Be on the lookout. Let's fix that out. On the lookout for perfect squares. All right? So, keep your eyes peeled. Ha 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 ha, I love puns. Anyway, so simplifying radical expressions that contain variables. Even exponents on variables are perfect squares. Odd exponents, except for 1 and the square root, except for 1 and negative 1, are products of perfect squares and a variable. So if I have like v to the third power, v to the third power can be written as v to the second times v to the first, right? Because there's an invisible 1 there. So I still have v to the third power, but I can actually pull out portions of perfect squares from my odd exponent stuff. So make sure you do that. So if I were to take the square root of 3, I could write it as the square root of 2 times v, and then pull out the square root of 2. Well, the square root of v to the second is just v, so I'm left with v times the square root of v. Yeah. That easy, but still someone's going to get lost. Anyway, so just pay attention to that. I personally know that I always forget to actually square root things, so keep me honest on this one, guys. All right, removing variable factors. So if I have the square root of 27 n to the second, I can write that as the square root of 9 times 3 times n to the second. Well, I can pull out the square root of 9, which is 3, and the square root of n to the second, which is just n, and I get 3n times the square root of 3. Ta-da! All right, number 2, I have negative 8 times the square root of 60a to the 7th. So I can pull out probably that square root of 4 and the square root of a to the 6th, because a to the 6th is really just a to the second times a to the second times a to the second. And I'm going to get negative 2 times a to the third times a times the square root of 15a. All right, well, there's a little bit of simplifying I can do outside of the radical, and that's just negative 2 times a to the fourth times the square root of 15 times a. Moving on. Square root of y to the second, or x to the second, y to the fifth. So, again, I have the square root of x to the second times the square root of y to the fourth times y, because again, this still equals that, right? Okay, so then I can pull out the square root of x to the second, which is just x, and I can pull out the square root of y to the fourth, which is y to the second, and I'm left with x, y to the second, times the square root of y. All right, So, multiplying two radicands, sometimes the product of two radicands is a perfect square. So just keep an eye out for that. Oh, I didn't fill that one in. Let's fill that one in. It was just kind of a silly little thing that I wanted to write up. Where was it? Oh, so like here's an example. Let's say I have the square root of 13 times the square root of 52. Well, that equals the square root of 676, and 676 is actually a perfect square, and it gives you 26. So again, just something to keep an eye out on. Sometimes this happens. So just be aware of that, all right? Just be aware of that. That can happen. So try everything, you know, be curious, plug something into your calculator. Maybe you have a perfect square in there somewhere. All right, application. Use the formula d equals the square root of 1.5 times h, or height, to estimate the distance in d miles to the horizon when h is the height of the viewer's eyes above the ground in feet. So estimate the distance of visitor to the Washington Monument, which some 8th graders will get to see, can see the horizon from the observation window, round to the nearest mile. So the Washington Monument window is 500 feet above the ground. So I'm going to replace h with 500, and I'm going to get the square root of 1.5 times 500, and that means the square root of 750, which can be broken down into the square root of 3 times 25 times 10. Well, I can pull out the square root of 25, so that would be 5 times the square root of 30, which is approximately 27.38. I should erase that because that is that. But since it wanted me to round to the nearest mile, it is 27 miles. So if I'm at the top of the Washington Monument, I can see about 27 miles. Cool, huh? All right. Next. So simplifying radicands with quotients. So if I take the square root of a fraction, basically, I can then square root the numerator and square root the denominator and get the same answer. The only thing is b has to be greater than 0. Remember, a and b can't be negative. Well, a can be negative and b can be negative because then a negative divided by a negative is a positive, but one can't be negative and the other one can't be negative, because if you have any negatives inside the square root, you're gonna have a problem. Okay? The only thing is if a and b are both negative, you're gonna have to pull out the negative before you go to this step. All right, so if a was negative and b was negative, you would need to be like, well, a and b divided by b ends up being a positive before you go there. Make sense? All right. And the same thing with a. Now, a could be equal to 0 because then it just means that you're taking the square root of 0 and you have a numerator of 0, which means you just have 0. But why can't b be 0? Well, then you would have undefined, and, you know, that only works when you got no slope. Anyway, moving on. So, 1, we have the square root of 90 over 5. That would be the square root of 18. If I divided before I took the square root, well, that's just the square root of 9 times 2. Square root of 9 is 3, so 3 times the square root of 2. Beautiful. All right, so next one. Dividing it out, sometimes it divides out that easily, all right? And now sometimes you might need to simplify the fraction instead of dividing it out. Well, if I have 48, the square root of 48 over 75, well, I can pull a 3 out of both 48 and 75, which gives me the square root of 16 over 25. Both of those are perfect squares, which leaves me with 4/5. So sometimes it's that easy. You just got to take a look at it and see which works. All right, rationalizing denominators. So, currently, at this point in your education, us math teachers don't want to see radicals as denominators. And that's okay. It's just later on in life, you're going to be told something different, and I'm just warning you that for right now, we want you to do this, but later on, you're going to be able to leave a radical as a denominator. Just letting you know that right now, I want you to do this, but later on, you're not going to have to. Okay? But for right now, please just humor Miss Teach. Okay. So, a radicand as a denominator that isn't a perfect square can be rationalized. To rationalize the denominator, multiply both the numerator and the denominator by the same radical expression. This makes the denominator a perfect square. So if I have 3 over the square root of 3, I can multiply both the numerator and the denominator by the square root of 3, which is going to give me 3 times the square root of 3 as my numerator, and the square root of 3 times 3, which is 9. So the square root of 9 is 3, so then I have 3 times the square root of 3 divided by 3. Well, what's 3 over 3? Well, that's just 1. So my answer is just the square root of 3. Crazy, huh? All right. So, number 2. I have the square root of 5 over the square root of 18t. And so I'm going to multiply by, well, actually, no, I'm going to simplify first because I'm really just trying to get rid of the square root. So I can pull out the square root of 9 on the bottom, which gives me 3. So now I'm left with the square root of 5 over 3 times the square root of 2t. And I want to get rid of the square root of 2t, so I'm going to multiply both the top and the bottom by the square root of 2t, which is going to give me some crazy stuff. But, you know, it turns out looking exactly like that as I ran out of space. But that's just because I'm showing a lot of work. A lot of you guys are going to be able to kind of just jump to the end. Now, I'd like to see a few of these steps just so that I can see your mental process. But, again, a lot of you guys are going to jump. Just don't forget to take the square roots. I'm one of those people, you know, I'm like, oh, I can pull it out. And then I forget to actually square root it to pull it out. It's a process. To get it out of the square root, you actually have to square root it. So make sure you take care of that. All right, I believe I have one more problem and one more slide. So the square root of 7m over 10 is that, and really there's not much we can do with this, and it's just that. Okay, so simplest form for radicals. All must be true. First, the radicand has no perfect square other than 1. Number 2, the radicand has no fractions. And the third, the denominator of a fraction has no radicand. All right, so make sure all of those are true. All right, I'm done, guys. Bye.